Okay, thank you for attending. My name is Meg Musa. I'm from Tetra Tech, and I'll be facilitating today's meeting. We appreciate your input in this process. It helps the agencies produce better solutions, so we thank you for your participation. So we appreciate you coming. Before we get started, I'll have the panel introduce themselves. Josh, we'll start with you.
I'm Josh Griffin. I'm Lake Erie Program Manager. I've been project coordinator source with PMDL for the last 9 months or so. And before we get started, I did want to let folks know we've gotten quite a few messages over the last couple of weeks about the comment period. We've been able to decide that we're going to go ahead and extend the comment period out to August 17th, 5 o'clock. So close of business on August 17th. So we get a little more time in for you all to take a look at the PMR and get the comments. So we have quite a few staff that aren't up here on the panel with us today that can help answer certain questions. There have been quite a few people that aren't here up front that have been helping out with TMDL. We have Ashley Ward and Walter Ayers from our central office at Permittee. Alex Smiley, Tom Hoffenbarger, Ryan Gearhart, some others. I see Peggy, I think. Peggy Christie's here as well. Shannon, Neighbors Chief of Northwest District Office, just got here as well. So we got quite a few folks from our Northwest District Office, and we've all been working together on this. So they'll be able to help answer questions, be here to talk afterwards, whatever. So from there, we'll go down the panel and everyone can introduce themselves.
Good afternoon, everybody. My name is Paul Gledhill. I'm a technical staff with the Division of Surface Water, so I help do some of the technical work developing this TMDL.
Can you speak a little louder so the people online can hear? I think we got it.
Good afternoon. I'm Matt Lane, soil scientist with the Ohio Department of Agriculture.
Eric Sauce, I'm the H2O Habitat Program Manager in the Ohio Department of Fisheries.
Good afternoon, everybody. I'm Bill Fishbein. I'm an in-house attorney with Ohio EPA's Division of Surface Water.
I'm Melinda Harris. I'm the supervisor of the TMDL program.
Okay, thank you. All right, the purpose of today's meeting is to discuss the content of the preliminary modeling results report and to answer questions from the audience. There'll be 3 presentations today on the topics listed here, followed by a Q&A after each. Okay, we'll get started with Paul Gledhill of Ohio EPA sharing the details of the source assessment.
Hi, welcome everybody. Thanks for coming. Can you hear me okay? I don't need to move the mic. Okay, great. So I'm starting off today. We're going to be talking about sources of phosphorus to the Maumee watershed that eventually make it to Lake Erie. I live in Central Ohio, and I just realized everyone here lives in Central Ohio. We had a lot of rain last week. Some parts of Central Ohio got up to 5 inches of rain. And I had a few friends of friends and one of my neighbors, their basement was flooded. And when I was putting these slides together, I realized there's kind of some analogy to flooding basements in what we're talking about today. When your basement floods, you got to get the water out, right? There's water in the basement, it's causing damage, you got to drain that. But once you do, then you get another problem. You got to deal with why your basement's flooded, right? You got to fix the sump pump, you got to fix the gutters. And so I think you'll see it's an imperfect analogy, but there's some similarities to kind of the history of phosphorus leaving the watershed and making its way to Lake Erie to this analogy. It's 2 different problems, but they're related, and we fix them kind of with different ways and in a different timing. So the PMR, I'm going to refer to our preliminary modeling results report as the PMR. It includes a pretty robust source assessment. We made an effort to include the best science available. There's a great deal of science, a lot of university, a lot of government science happening right in the Maumee watershed and in the greater Western Lake Erie. So the idea is we wanted to put as much science, as much relevant recent science in the report, so then we can recommend the most effective phosphorus reduction actions. I am going to talk about some of the kind of the overall phosphorus trends, and then we're going to hit some highlights from that source assessment, which is in the report. So this is literature published. it's looking at trends of phosphorus. This is phosphorus delivered from the Maumee watersheds at the Waterville monitoring station. There's 4 figures here. On the left 2, we're looking at total phosphorus. On the right 2, we're looking at soluble reactive phosphorus. Now, soluble reactive phosphorus is almost the same thing as dissolved reactive phosphorus that we talk about. And I just kind of refer to it as dissolved phosphorus here. Now, dissolved phosphorus is really important, right? Because this is the most bioavailable for the HABs, the harmful algal blooms that we're seeing in Western Lake Erie. So I want to draw those. Okay, so on the tops are concentration, the bottoms are loads of those parameters. Have a look on each of these figures. You'll see these kind of hollow circles that are much more orderly than the kind of the scatter behind. This is an analysis done to normalize the noise of these figures. You'll see a lot of the phosphorus delivered to the Maumee is from non-point source pollution. And non-point source pollution really varies each year based on hydrology, right? How much it rains and then how much stream flow results from that. This is a really cool statistical method, this flow normalization method that produces these little dots. And it allows us to see trends a little more clearly. So if we look at total phosphorus and the load here, you see in the late 80s and through the early 90s, there was this really significant reduction of total phosphorus. Now, this addressed some really big problems in Lake Erie. We had really big green algae blooms in the 70s and earlier. Those algae would die. We'd have hypoxia or dead zones that would result in fish kills, really nasty stuff, recreational issues. It was a problem. And in fact, when we saw this reduction, a lot of folks declared like this is a success story. We really addressed Lake Erie's problems. However, if we look at either one of these dissolved phosphorus figures, you see there's this rise in concentration that happened about 20 years later. It started kind of in the late 90s and it went through the mid 2000s and it's leveled off, but it's leveled off at a too high level. And science has told us that really it's this dissolved phosphorus increase. That's what's brought about these harmful algal blooms. It's a different type of algae in Lake Erie, and we know that this is a problem. That's what this TMDL is here to address. So most folks have probably seen this. This is from Ohio EPA's nutrient mass balance report. This is where we look at kind of the total phosphorus being delivered to major tributaries in Ohio. This is specifically looking at the Maumee. And we break the sources of those phosphorus into kind of into 3 coarse categories. So on the bottom of each of these bars from 2013 through 2019, that's what we're calling NPDS, the National Pollution Discharge Elimination System. It's our permitting system. And specifically, this is our wastewater treatment plant facilities. So these are your municipal waste, treating human sewage, a lot of large industrial facilities that deal with food waste primarily. It's a really small amount of these bars, right? On average, it's about 6%. And you'll see it doesn't vary that much. Now there's HSTS, that's household sewage treatment systems. That's your septic tanks, folks that are not on public sewers, right? We have different methods we can use to figure out how much phosphorus they're contributing that make it to the Maumee and Lake Erie. This represents about 2%, a really small portion of the total phosphorus the Maumee delivers to Lake Erie. And again, you see it really doesn't fluctuate year to year. What you can't miss on these bars, right, is this dark red, this what we're calling NPS. It's non-point source. And so this is the phosphorus that comes from everywhere else but those 2 sources I just mentioned, right? On the land. It's coming from people's backyards. It could be coming from nature preserves to a small degree, and it's certainly coming from agriculture as well. One thing you'll notice is this is a very huge, large mass majority, right? It averages 92% of the total phosphorus, but it really varies a great deal every year. And that's because what I just mentioned, hydrology really dictates non-point source. If we have a dry year, we don't have that much rain, and we don't have that much runoff, and the streams don't go up that much, and they're not carrying that much phosphorus. But these wet years like 2019, they're carrying a great deal. This figure also shows this 2008 baseline. So this is the total load of total phosphorus that was delivered in 2008. This year has been used kind of as the baseline by it's a binational group, the Great Lakes Water Quality Agreement. It's their Annex 4, their nutrient annex. And so they said, this is our baseline. We're going to set for where we're going to make targets to how to address the HABs. And in fact, this red horizontal line, that's the total phosphorus target that the Annex 4 group has set to say this is what we need to get to for an acceptable bloom, for an acceptable size, smaller blooms. We explained that in our loading analysis plan. That was the last report. And so that's the target we're using this in today. So I'm going to talk about some first non-point sources, and we're going to hit these highlights. There's others in the report. Encourage you to read about them, ask us questions, and please send in comments. And the first one of these we're going to talk about is agricultural fertilizers. So the Maumee is a very large watershed, and it is a row crop dominated watershed. About 70% of the land in the Maumee watershed is utilized by row crops. There's a great deal in the report about why we use fertilizer. We need a productive crop for the food we all eat, right? What fertilizer is used? And you see on the top here, there's commercial fertilizer that's often sometimes talked about inorganic or mineral fertilizer. And then there's manure. We know manure is also used as a fertilizer in the Maumee watershed. So there's a great deal of information in the report about just why fertilizer is used, what it is. We wanted to highlight right here on this slide, there's a figure. This is from the Tri-State Phosphorus Recommendation. And this was updated, I keep getting it wrong, Matt, last year or 2 years ago? 2 years ago. And we think that it's important to note that there was a couple things in the update that really should help the amount of phosphorus going on fields. You see here, this is soil test phosphorus on the x-axis. I'm going to have a few figures to show, a few more at least. And so as we get more phosphorus dissolved in the soil, then it's recommending less phosphorus be applied as fertilizer, right? That makes sense. Well, it used to be once we hit this maintenance level, there was still some phosphorus being recommended. They called that the drawdown phase. And so the new update of the Tri-State recommendations, they got rid of that drawdown phase. As you see here in the bottom, there's no agronomic reason to apply fertilizer. Also, Matt Lane, I pointed out because he from Department of Agriculture was on this group. The group that put this together, they lowered the amount of phosphorus that they calculated being taken off by crops, and that results in basically you don't have to put as much on. So this black line basically got lower from the previous recommendations. So I mentioned commercial fertilizer and manure. Those are the two things used, and there's been a lot of attention on manure, right? Folks have probably seen this slide, and the next one I'm going to show. Department of Agriculture produced these last year, and this is showing the animal units by the thousands, specifically in the Maumee watershed in Ohio. And as you can see here, every 5 years, there has been an increase since 2002. Department of Agriculture in Ohio, they use national statistics on livestock, and they added a lot of value of what the information they have on this. So we know there has been an increase, and this is from the confined farms increasing and growing in Ohio. The Department of Ag has also kind of put this in perspective. When we go back to the 50s, we had a great deal more livestock than we did at this base here around 2000 when we started to see this increase. Now, however, we do know that the livestock is kind of in a different form now. We have larger farms, and we don't have these small pastures and things where everybody had some animals, right? They're more in these confined feedlots. So we know we have more livestock. What's it mean for fertilizer, right? What's it mean for that livestock manure being used as fertilizer? This is some new analysis, this slide and the next, that Department of Agriculture has done just this year, and we think it's the first time published in our PMR report. So the green triangles here, this is showing how much phosphorus is being removed by crops. So each one of these triangles represents one farm year, right, in the Maumee watershed, average for the whole watershed. And what you'll notice is when we go back to 2008 through 2020, there's been kind of a steady increase in the amount of phosphorus removed by crops, okay? It's a good thing. It probably indicates farms having better yields, being more productive, and potentially more farming as a whole. Now, the blue dots on this plot, these are showing the amount of fertilizer phosphorus that is applied from the commercial fertilizer, not from manure. And there's the trend is going a different direction. We're seeing a decrease in that trend. So let's put manure into this, right? Department of Agriculture, what they did was they did this analysis where when we're looking at the amount of phosphorus taken out by the crops and then added as fertilizer from commercial and manure combined, they kind of set the baseline. And if that were even, that would be a 1.0, right? The same amount being put on is being taken off. And they did this analysis again going back to 2008. So you'll see here, there's only 3 years where the Maumee was above that 1.0 line. So only 3 years, there was more phosphorus put on as fertilizer than was taken off from the crops. In the rest of the years, there was more phosphorus being removed from the fields than was added as fertilizer. So overall, what does this mean? There's an ag soil drawdown of phosphorus. And this is a really good thing, especially here when I talk about legacy phosphorus in a few slides. It also is telling us we saw a decrease in commercial fertilizer, and it seems like the manure is taking that up, right? So it's being offset. Manure is offsetting the reduction of commercial fertilizer. And the good thing is we're not seeing too many years above the 1.0 line, right? So we're not producing more phosphorus than we can handle.
Putting this all together, Ohio Department of Ag's various analyses, as well as other independent work, has found that manure supplies approximately 20% of the crop's needs for phosphorus in the Maumee watershed. So that this middle point on this slide is really important. And several studies have looked into the impact of phosphorus losses from agriculture fields from when they have manure used as a fertilizer or when commercial fertilizers have been applied. And most of these studies have found no difference. So that's to say, the type of fertilizer that's used does not appear to increase or decrease the amount of phosphorus that is exported to streams. Now, I'll add here that we're not talking about manure being directly discharged, dumped into streams. When this happens, it's due to an accident or mismanagement on the farm, and direct discharges of any type of fertilizer into streams is unacceptable. And we have Matt Lane here from Ohio Department of Agriculture. He can explain the various rules and guidelines that apply to different operations and their fertilization styles in Ohio. So, in summary of this section of our talk, livestock populations have increased in the last 2 decades, but we've seen a shift in the fertilizer sources where there's really no net increase of phosphorus applications throughout the farmland.
There we go. I'm going to shift a bit and talk about agricultural soils and legacy phosphorus. So there's been a historic conservation reduction, and it's really been focused on soil loss. That's your no-till, minimum till. NRCS, which is one of the arms of the USDA, they've calculated up to 60% of the total phosphorus that used to be delivered to Lake Erie has been reduced thanks to soil conservation. There's also this thing called legacy P. So legacy P, it has a lot of different definitions in the literature, but basically it's when phosphorus gets accumulated in soil to a degree that's more than the soil needs. We know, so past management, there's been an over-application perhaps, or the crop didn't take off enough. There's more phosphorus there than it needs to be. So what the literature is telling us in this bottom bullet here is conservation tillage has kind of changed the nature of phosphorus, the nature of soils. And then also, I'll mention a few slides, changes in hydrology. It's created this environment where DRP, specifically the dissolved portion of the phosphorus, is moving much, much more. And we really think that's part of the answer to this increase of DRP that we're seeing. So again, soil erosion, it was a very good thing, the soil erosion. This was draining the water out of the basin, right? Dealing with the most immediate problem with all of the sediment, choking the streams and getting into Lake Erie. I mentioned on the last slide, about 60% of the total phosphorus has been calculated, have been reduced. Same folks, they calculated 80% of sediment. So there was that much more sediment getting into the streams. Phosphorus can bind to soils. That's the particulate portion of phosphorus, the other side from dissolved phosphorus. So that makes sense why when we hold back a lot of soil, we're seeing the particulate phosphorus stay put. But then it seems like it's resulted in this situation where dissolved phosphorus can leak out much more easily. And this last point is just dissolved phosphorus increases due to soil conservation. It was an unintended consequence, right? But it was predicted. As far back as the late 70s, early 80s, there were researchers saying, yeah, we got to deal with the sediment loss, but we might see dissolved phosphorus start creeping up if we do this. And it seems like that is what we've seen. So I want to talk about that phosphorus movement, but first, just need to stress, it's a very excellent environmental and ergonomic benefit that we've held soil back. I mentioned Lake Erie, all the problems at Lake Erie in the 60s and the 70s. In our streams, we used to see so much more sediment in the streams. There's been lots of research documenting these improvements in what we call the near field. These are two fish that are very sensitive. Oh, I put a laser pointer right on that guy's gill. There's two fish that have been found throughout the Maumee watershed now. They're extremely sensitive to sedimentation. We didn't see those. A few of them were spotted in the 20s, before modern agriculture took off. They had not been seen for 30, 40, 50 years, and now we're finding them throughout the Maumee. So it's a great success story. We don't want to go back and stop conserving soil, right? We need to deal with this new era of phosphorus leaking out. So Dr. Sharpley from USDA's Agriculture Research Service, he really pioneered a lot of talking about legacy phosphorus and what happens. This figure shows the amount of soil phosphorus, so dissolved phosphorus in soils, and then how much phosphorus runs off. And so as you see here, the more phosphorus, the more enriched the soil is, right? The more runoff we have of dissolved phosphorus. Kind of a no-brainer. But we learned some neat things from this research. When you have kind of sandy loam soils, it can hold more phosphorus. It can allow phosphorus to run off more, and versus the silty loam and clayey soils. But really, what's really interesting from this work is notice this inflection point where the slopes change. And what this is kind of showing a threshold effect. When we have enriched soils, they're going to release phosphorus. When they get to a certain point, they go over this threshold, we lose proportionally more phosphorus. And that's a problem. And that tells us we really need to understand where we have these high soil phosphoruses. And potentially, most likely, based on what we saw from ODA, from legacy, from previous past fertilization and actions. So a lot of research has gone into this. We learned a really neat lesson. 2019 was an extremely wet year. A lot of, and as was the fall in 2018, a lot of fields did not get planted. They went prevent plant, and therefore they didn't get fertilized. And what's really cool is that the researchers that did this, some of them were out of Heidelberg, they were able to show that there was this almost immediate reduction in dissolved phosphorus because so many fields weren't fertilized. But they didn't see a proportional reduction in dissolved phosphorus as the reduction of fertilizer, right? So we know that there's still phosphorus available that's leaching out from this kind of like real world experiment that occurred throughout the entire really Western Ohio. There's been a lot of SWOT modeling that looks at the sources of phosphorus. We've talked some about this CAST 21 study. It tells us about 20% of DRP, 40% of total phosphorus is coming from these soils, from this legacy potentially. But it has been noted that we can always model and remodel and improve modeling. That modeling didn't do as much as understanding where potentially some areas have higher phosphorus, some fields, just part of the fields have really high phosphorus. So we're excited. There's a lot of new studies. There's active studies happening right now. OSU is working really hard to do a better job at putting the distribution of soil, the real distribution of soil phosphorus in their modeling. Another OSU effort led by Dr. Jay Martin, they're doing something really innovative. They developed this thing called a public-private partnership to work with farmers to understand soil phosphorus. So if you're a farmer, if you have a farm and you do soil testing, that's your data. That's proprietary data. You don't have to share that with researchers. You don't have to share that with the government, certainly. And it behooves them oftentimes to not share that. So what Dr. Martin and all of his colleagues are trying to do is they're setting up a firewall, a way to learn about the farmer's data and study and research it, but still protecting their privacy, both geographically and business-wise. So some really great research coming out to help us understand this, and we think that this has been steering what we recommend for reductions, but we wanted to share with you how important it is going forward with the TMDL. Okay, a few more sources I'll talk about. There's oftentimes it comes up stream bank erosion as a source of phosphorus, right? We certainly know erosion can happen, especially when stream banks are unstable, when potentially there's been a disturbance either actually to the channel or just in the watershed alone. Sometimes that can cause an instability of the channel. But there's a wide variety. The research is all over the place. There's this really good study that I wrote about in the report from Fox, where he went through every study that's looked at stream bank erosion. And he said some watersheds, they said 6% of the total phosphorus is from stream banks. Some watersheds, 93%. So it went from almost insignificant to the most important thing. There's also some new work from Iowa that says it's kind of somewhere in the middle. So we know stream banks is part of the equation, but there's still a lot of scholarship and understanding on that. Luckily, there's also a lot of research ongoing in the Maumee that we discussed in the report. We do know that conservation buffer strips and just backing off of ditches, not in streams, not doing land uses close to them. There's research that says that really can reduce the amount of stream bank erosion and phosphorus from that. And just in general, there's lots of research out there. When we do the traditional trapezoidal ditch, when we have ditches explicitly for drainage to move water as fast as possible, we're losing a lot of, not only does that eventually become unstable, right? And we lose phosphorus from those banks, but we also lose a lot of services that streams might be providing to reduce phosphorus or just to trap the phosphorus within. So I mentioned hydrology a few times. Obviously, I think it's pretty logical, right, that it really drives an on-point source. So you got to have that water energy to move it off and take it into the streams. Yep. Okay. So ARS, Agriculture Research Service, based in Columbus, they've done a specific study of the Maumee. This is the Maumee watershed right here, and they did a really detailed look at rainfall and stream flow. So they found about 12% increase in rainfall between the mid-70s to around 2020, and that resulted in 20 to 30% increase of stream flow. So that's a challenge right there. They did note that in the southern part of the watershed, specifically the southwestern part, St. Mary's and the Auglaize, they're seeing more of an increase there than the northern part. And the study documents how this increase in rainfall has come with heavy and very heavy rains. So this all has implications, and it's not good, right? It's it's potentially part of this piece of this increase in DRP. When you have a saturated system and then you add more water, that really helps that leaking out of dissolved phosphorus from the soils. And the soils are more staying put than ever. This is analysis that's very similar to something Heidelberg did, but we did it in-house. And we're looking at spring discharge. So spring discharge, that's just how much water moved through the Maumee, right? It's the total volume of the spring season, the March through the end of July season. That's on the x-axis. And then the y-axis is looking at the spring DRP load, the mass or how much weight of dissolved phosphorus was delivered to Lake Erie. And you see, if we follow these red dots, this is 1983 through 1999. It totally makes sense, right? The more water we have, the more water that flows, the greater the load of discharge that we see. What's really striking is from the last 20 years, 2000 through 2021, see the same trend, but notice the slope is steeper now. We're getting more DRP load delivered than we are per unit of volume of water. So that's an issue. That's part of this problem, we believe. And there's another thing that's really noticeable on this. These 5 years here, these 5 years they still follow on that same trend. But what we're seeing is, and actually, I think this is, well, I don't know which year that is, I won't say. But these are 5 years that had more rain and more stream flow than we've seen all the way back to 1983. So this is just another way of looking at it. And it's also showing that we do have this increase of hydrology that is real. The report also kind of goes into some in-stream processes. I mentioned a little of those when I was talking stream bank erosion. But what happens actually in the channel, we know it can change the amount of phosphorus. Some phosphorus can sink, get trapped, and then sometimes streams can actually be a source of phosphorus. A lot of factors play into this. There's a lot of bio, geo, add more O chemistries that go into it. But it's a fascinating realm of research. There's a lot of active stuff. Out of OSU, Dr. Jim Hood, he's got a really great paper, and there's been a few others that kind of are in the same mold, where they look at what this on the left we're looking at here. So Dr. Hood proposes that kind of the current model of thinking about streams is that they're a pipe, right? What comes off the field and enters the stream up in the watershed is the same thing that enters Lake Erie. So here, the same amount of sediment coming off the land into the river makes it to Lake Erie. The same amount of DRP, dissolved reactive phosphorus, makes it to Lake Erie. He's done some really neat experiments where they've actually seen during high flows, not low flows where maybe there's not that much load that we're worried about, but actually during high flows where we have sediment, right? It's high flow, so the streams are getting muddy, there's turbidity. The sediment actually flowing through the water is sorbing. It's actually adhering some of the phosphorus, the dissolved phosphorus. So what this means is, as we go downstream, the dissolved phosphorus is reducing. We're seeing what's generally referred to as an environmental service that the sediment is giving, reducing the phosphorus. Now, think back a minute ago, we said in the last 20, 30 years, we've really reduced the amount of sediment going to the streams, right? So if this model holds up, if this has actually been happening, where sediment in the streams is reducing the amount of dissolved phosphorus that gets exported, that service has been lessened, right? We don't have as much sediment, so we have less of this service. And it makes sense that this could be a piece of the puzzle, why we've seen these increases in dissolved phosphorus. So a lot of great research, and I said that. These are all challenges, that we're trying to deal with. These are things that we put forward. We're showing the most advanced science we can in the report, and we hope that can spur what we recommend for reductions. Now, I want to talk about point sources. These point source folks over here. Just real quickly, we talked about 6% of the total load is coming from municipal wastewater treatment plants and some of the industrial plants that do treat with phosphorus, food waste, and et cetera. This pie chart kind of shows what that 6% looks like. About 50% of this wastewater treatment plant point source load is from our major municipal plants, basically the larger cities. This other large chunk, these are just all of the point sources in Indiana and Michigan. And let's have a look at those loads. So this is looking at the wastewater treatment plant total loads. 2008, we had about 70 metric tons of total phosphorus from those plants. It's reduced a little bit. It's around 60 today. But what I really want to draw your attention to is this horizontal blue line way up here on the kind of the ceiling of this figure. And this is what we're referring to as the authorized load. So the majority of the flow, the vast majority of this wastewater effluent that comes out is from plants that are required to treat for phosphorus. They have total phosphorus limits. Most of those limits are 1 milligram per liter. It's a concentration limit, right? Now, and then all of these facilities, we permit them at a certain design flow. So your facility is designed to treat so much water, so much volume. So if you multiply that design flow by this concentration limit that we've given them, you cannot exceed 1 milligram per liter. That's what comes up with this authorized load. So it's a little over 150. So you see the current discharge of these facilities is well below, it's below half of what we've authorized them to discharge. So that's a great thing. We've had questions like, why are they so much below the authorized load? Well, a lot of them aren't realizing that total flow. They're not at their design flow, right? They're not discharging as much. But some of them are actually going to them above and beyond. We're seeing their discharges well below 1 milligram per liter. So a lot of that's through optimization of the technology. So they have technology in to treat phosphorus. They know they have to treat phosphorus. They're able to fine tune their treatment and a lot of times without even costing them that much more to reduce phosphorus even lower than what we require them. There's also been more restrictions on phosphorus in laundry soap and detergents, and that's helped. And then many facilities, especially in Northwest Ohio, have wet weather discharges. This is the combined sewer overflows, and then there are some bypasses. And Ohio EPA has worked with all of these communities to come up with a plan. We have to reduce these. And with the bypasses, all of them, and a lot of the CSOs, the plan is to eliminate them, zero discharge. And as money and infrastructure is going in place, we're seeing reductions from phosphorus contributions from those sources. One slide about stormwater. So stormwater acts a lot like non-point source, right? Because it's driven by hydrology. However, a lot of the stormwater in this watershed and most watersheds is actually regulated under the NPDES system. So it's facilities have stormwater provisions in their permit, or some municipalities actually have what's called MS4 permits. So when a stormwater is regulated, then that falls into the point source category of a TMDL, right? That's how the Clean Water Act dictates that we deal with that. So we discussed those. We kind of have two sections on stormwater in the PMR, one the unregulated, but we really save most of the talk forward within the regulated portion of it. There's more impervious surfaces in developed land, right? There's more roofs, there's more pavement in general, and so that makes for more total discharge, more water relative to natural areas and agriculture areas runs off. And so that has a chance of bringing more pollutants, more phosphorus, for instance. And we know the sources of phosphorus in these developed lands are in general like yard waste, pet waste, and road grids. So we have some documentation and literature on that in the report as well. And the last source I'll talk about is the household sewage treatment systems. Like I said in the get-go, it's about 2% of the total watershed, so it's a pretty small percentage of the load. It's important to kind of mention, these are homes that are not connected to a municipal sewer service, right? So they have the septic tank that we think about. That's where solids settle out. But in fact, there's two kind of major types of systems after the septic tanks. We have these discharging systems. That's where the decant from the septic tank, it goes into oftentimes another vessel that aerates the waste. And that's good for reducing ammonias and cutting down the carbon waste. We call it biochemical oxygen demand. But it does result in some phosphorus. At the end of this aerator, there's a discharge. Now we have on-site systems, and that's where we have our septic tank, and then the decant is just distributed through the soil, your leach field, if you're familiar. So we'll see less of a phosphorus loss from that. In fact, hopefully no phosphorus loss from those. That said, both types of systems can be deferred maintenance or just completely failing. So we can see phosphorus from these systems in both ways. So the last bit I'll talk to you about is within the PMR, we do have a chapter on critical source areas. The Maumee watershed is a very large watershed. There's geographic, there's land use differences, and we know that does result in some disproportionate loading. Some areas are discharging more phosphorus than other areas. This is from some modeling work. It's an ensemble modeling work. So they took a SWAT model from one university, another SWAT model from another university, put it on top of that in several layers, and they said, which watersheds, which small watersheds are we seeing that are the hottest, that are contributing proportionally more phosphorus? That's a really great way of looking at this. There's also these water quality gauges. I've talked about the water fill gauge. That's where Heidelberg is at a USGS streamflow gauge. This is a continuous streamflow. They're measuring streamflow every minute of the day. You can go online and look at it. At Waterville, they have an automatic sampler, a refrigerated sampler, and it takes a sample 3 times a day. In Heidelberg, we'll run at their lab 1 or 2 or 3 samples every day. So we really know the amount of nutrients moving through there every single day. There's over 20 of those type of stations throughout the Maumee. We've been really pushing to understand our watershed better with this continuous monitoring data. This is kind of the gold standard of data. The different colors here are just Heidelberg maintains some of these water quality stations and USGS maintains some of them. We have these at every major tributary, so the Tiffin River, the St. Joseph, St. Mary's, Yawglaze, Blanchard, Ottawa. And we have several what we call sentinel sites. So these are smaller watersheds where we know there's some unique land use. There's maybe some unique best management practice in place that's happening down here in Wood County. We're learning a lot from these. Waterville's been around since the 70s. With a lot of these other sites, we've only had 5 to 10 years of data. So we're just now starting to really dig into the data. And we presented quite a bit of an analysis on these stations. This is just one example of that analysis. One thing we've seen from these stations is in the southern part of the Maumee, there is proportionally more phosphorus being delivered. And if this slide is showing all these different stations in different years, we're looking at the dissolved reactive phosphorus concentration for the season, flow weighted mean concentration. And these gray diamonds, these are the southern sites, and the black circles are the northern sites. So you see in most years, most of the southern sites are higher than the northern sites. We discussed that in the report. So you'll say, hey, wait a minute, Paul, some of these northern sites are pretty hot. We discussed those in the report and what we're learning from those. We need reductions throughout the entire watershed. Almost every site is still above our target concentrations. But this work is showing us that there's some areas we can expect more reductions, and we hope that this can guide where we recommend best management practices, water retention practices, and so forth.
Next, we have Josh Griffin of Ohio EPA sharing the details on the results and methods of the calculation. Methods and results. Calculation.
So my battle with these, I have my glasses. I need them to see you guys and your faces out in the audience, and I can't read my notes as good with them. I need some kind of bifocals where I don't have any help up here. So I always trip over that. But anyhow, so for the TMDL, we chose to use the mass balance model, and it's a model that Ohio EPA is familiar with. It's something that we first developed in-house for the 2016 nutrient mass balance study. We've done multiple iterations of that study, and we also used it to help with the development of our domestic action plan and publish some mass balance modeling work in the 2020 domestic action plan. Those models had their purpose and their reason, and we had to do some additional tweaking and accounting to adapt this type of modeling to a TMDL. But ultimately, a mass balance model is an empirical model. And here we really rely on the high quality data we get out of the Waterville, what we call 4-point in the mass balance modeling world. So we collect, Heidelberg has been for over 40 years now collecting daily phosphorus loading data from the Maumee watershed. So it gives us a good anchor point where it gives us a good anchor point to rely on for this empirical type of modeling. So for developing the TMDL, we aren't relying on a mechanistic model, and we aren't making really as many assumptions about what the load actually is coming out of the Maumee River. So to develop the mass balance model, what we do is we have a host of sources that we have a lot of information on, and we can make fairly robust estimates of the phosphorus discharged directly from those sources to streams in the watershed. We have specifically looked at kind of a suite of facilities in the watershed. We have our municipal wastewater treatment plants. Paul kind of talked about these a little bit as well. We recognize that some of the reverse osmosis treatment plants do have some phosphorus in their discharge. We have other industrial facilities that contain phosphorus. Like Paul mentioned, a lot of times these are kind of food processors or industrial facilities that are also using biological treatment processes to treat their wastewater. And then, beyond the individually permitted facilities, we have general permits that are associated with treating sewage or sanitary waste. We primarily have 2. We have one for small sanitary systems. Those are less than 25,000 gallons a day. And we have one for our household sewage treatment system. So, HSTS, those are all under 1,000 gallons a day of a design capacity. Paul, we recycled this slide here, just to bring this imagery back, we have the two different types of household sewage treatment systems. Those calculations and how you estimate the loads from them are different. Paul mentioned, we don't get a lot of phosphorus reduction from a system that, aerates the waste and discharges it to a stream, but we get a fair amount of phosphorus reduction from facilities that disperse their wastewater to the soils on their lot. So for the non-point source, then, for the TMDL, we're looking at that 2008 baseline year. So to get our baseline loading conditions. For the non-point source load, the mass balance is a conservative model in that we assume that the phosphorus delivered to the stream is delivered to the watershed outlet. We do understand that there's a lot that may happen in that interim, but on average, those in-stream processes, those are happening regardless of where that phosphorus came from. So kind of as things kind of move through, we make this assumption that there's kind of net delivery of things that reach a stream channel. So to get that estimate, we take the total phosphorus load at the Waterville pour point, and we subtract out the phosphorus load from the household sewage treatment systems and the treatment facilities. From there, we divvy that remainder load out into three categories for the landscape. We have developed land, agricultural land, and natural areas. And so those initial calculations then have all of the phosphorus delivered from the landscape, and we don't differentiate, where the source of stormwater is from. But because we're developing this for a TMDL, some of the load from those stormwater areas is regulated under the Clean Water Act. We have to account for it as a waste load allocation in the TMDL, as opposed to a load allocation on the non-point source side. So generally, that stormwater is covered by 4 different permitting, or representing kind of 4 different major areas. We have the large MS4 community. We have one in the watershed in Toledo. We have the small MS4 general permit. So these are small communities associated with the urbanized areas that didn't meet the thresholds for that large area. We have industrial facilities that have stormwater requirements, both through a general permit and in their individual permits. And we have construction stormwater. So we know where those permits are. We know what those facilities are, where those communities are. So we went through and, rather than just kind of making some assumptions about how much there are, we digitized their approximate footprint, and we used looked at their permits to look for acreages. And we were able to use that area to kind of divvy out the load for the stormwater that is under our permitting authority versus the load for stormwater that is not regulated. It's from smaller communities or facilities that don't have stormwater permitting requirements. And another thing we did is we wanted to look at, another thing we did with the mass balance model is we added some weighting factors into it. And this is similar to what we did for the domestic action plan in 2020, and that we wanted to be able to better account for, if we use this mass balance model to help us inform implementation, we wanted to be able to better account for where phosphorus was coming from regionally. And, one of the things that came out of some of the SWAP modeling efforts is like, what's really driving the loads? And in conversations with some of the modelers, it's like, well, it really comes down to, on average, how much water is there, and what's on the landscape. So where we have more agricultural land, more row crops, we see more phosphorus loading, and where we have higher stream flows and discharges, we have more phosphorus loading. So if you account for those two things, on average, across the landscape, you're going to have a decent understanding of where the load's coming from. So we wanted to use, we wanted to use the loading information we have at these gauges further up in the watershed to kind of look at it and kind of evaluate the efficacy of this mass balance type of approach for evaluating phosphorus on this large watershed scale and kind of understanding these kind of broad landscape trends. So because it's empirical, we can't do much to compare our loads, and it's directly indexed to that Waterville gauge. We can't do much to compare our results to the Waterville gauge. Our loads equal exactly what is at the Waterville gauge in any given year. It's forced to be. So we can't do anything statistically at that scale. But we do have these other stream gauges. We have multiple years of record now, so we can kind of look at the distribution and kind of relative patterns in loading from those gauges, and we can see that generally our watershed model is performing. Not generally, our watershed model, mass balance model, is giving us the trends we would expect to see across the landscape at this kind of regional scale. So to take that to the next step, we have our baseline model built in this instance now, and we need to kind of say then, okay, how are we going to divvy out the load so that we can show, we can have a set of allocations, loads that add up to our target condition. But you can't do that without thinking about, well, how can we actually get there? So we kind of developed the allocations and implementation plan kind of, or at least the scheme and framework kind of tangential to each other. So we're thinking about how these things can happen, what impact it would have as we look at different options for allocating loads. And ultimately, the TMDL has to have three components. We have to have our waste load allocation, so that's our point sources. We have to have our load allocation. We have to have considerations for our margin of safety. And beyond that, we need to think about, especially on the point source side, as facilities grow, communities grow, new industrial facilities might be come into the watershed as we see, economic development work. We need to be able to thinking about that as well. So we kind of got to think about allocations. We're thinking about implementation too. We're going to talk a little bit more about the actual implementation framework after we take a break for questions here in a minute. But thinking that those two things are kind of happening in parallel.
So as that happened, we wanted to highlight some of the key decisions that were made in the PMR that affect the allocations. 3% of the target load is reserved as an explicit margin of safety. This is in addition to conservative assumptions that provide some implicit margin of safety in the TMDL. Treatment facilities have a historical record of reductions in DRP loading. Changes in the MOMI have largely been linked to changes in non-point source loading. The TMDL set the allocation for treatment facilities based on the 2008 baseline, because while these sources were not the driver of water quality changes, increasing loads is incompatible with ongoing efforts to manage non-point sources. Implementation of long-term control plans results in high levels of control from the source, with large reductions in discharge volume being realized. These are allocated at the level of control expected from the long-term control plan. The stormwater load from MS4 communities is reduced 20% from the 2008 baseline. Communities have been strong partners in non-point source planning efforts, and wetland construction, stream restoration, and other landscape improvement activities are better managed through non-point source planning efforts. The HSTS allocations assume that half of failing systems are repaired. Nearly a third of systems in the watershed have been identified as failing in the past by the Ohio Department of Health. We need to continue to move the goalposts and improve treatment in this part of the landscape. The remainder of the target load is allocated to non-point sources. This is much like the method for determining the baseline, where the mass balance allocates is based on the subtraction of the known quantities from the total to set the targets for non-point sources?
I briefly mentioned that, we're going to need to think about some novel permitting schemes, some of the things that we need, to implement this waste load allocation for the point source community in a way that, allows us to continue to perform where we're at, and also provide some flexibility, but make sure that we are kind of managing those existing loads. And, conceptually, this is where I said it gets kind of messy. We have to do these things kind of in tandem. So we have to look kind of forward to our implementation. We're proposing, and I'll talk a little bit more about it later, a general permit for phosphorus for a group of facilities. So it's the largest facilities in the watershed. And then within that group, you kind of look at that load, that opportunities for reductions are kind of different, and their capacity based on size and treatment type might be different. So, there's an economy of scale for our largest facilities, and we're only really doing this because the TMDL requires an individual allocation in addition to just a total waste load allocation. So we have to kind of say, when we do these individual allocations, is there a way to do it that is still respective of, the capacity of these facilities to potentially do better? But ultimately, we're going to implement it through this general permit. So we wanted to have some equity baked into how we distributed these loads. So, largest facilities have some economies of scale. So the individual allocation is lower for those. The smallest facilities, it's, their capacity to put the technology in place is a little more limited. So we kind of set that. And then we kind of solved for the facilities in the middle, and got a concentration that lands somewhere in the middle. So, we do have these individual allocations in the TMDL. It's not our intent to put these individual allocations in individual permits. Rather, we're going to pursue this general permit concept. But they're required for the TMDL. You'll see them. There was a scheme to how we kind of divvied them up. So that's if you see, there's a lot of work that goes into those in the report. But it's not our intent to move forward with those individual allocations in individual permits. Back on June 1, we had a webinar. That webinar is posted online. There's a recording of it. The slides are up on the webpage. We went through kind of our framework for an implementation plan and adaptive management there. I'm not going to dive back. I'm not going to go back through all of that information today. It looks very similar to that. I want to point it to you if you didn't get to catch it. If not, you should be familiar with some of these concepts. But I do want to add a little, I think the report added, compared to what we talked about back on June 1 and what's in the report, there's a couple of places where we've added some additional details. So I'm going to focus largely on developing the strategy and implementing the strategy today, because those kind of, it's like, what do we think we ought to do, and how are we going to do it? That's kind of what the report has in it. And before we get there, one of the things with implementation and this TMDL, maybe more than any other TMDL that I've been involved with, is that, we aren't at the beginning. We've recognized this problem a long time ago, and we've started to build some of the framework for how we're going to start getting to where we ought to go. So we're going to, in the report, we kind of look to that to build some of the infrastructure that we need. But we do add some pieces on how we can maybe do a better job tracking things across the landscape. So the TMDL is going to add some substantial value to those implementation plans and strategies that are out there, in addition to adding some additional information. So ultimately, one of the things, we didn't maybe get too far into, because we weren't diving into numbers today, is, we have, that was only a portion of the Maumee River watershed. So we have the entire watershed has a loading target. But the TMDL, we allocated loads outside of the state of Ohio as a boundary condition, and we'll look to the other states to implement their plans and strategies how they see best fit to allocate sources within their state. So we're not bifurcating that load down to the level we have or for Ohio. So we make this first kind of high level cut, what's our share of the load in Ohio? So we had, it's around 2/3 of the load. It's approximately equal to what the area of Ohio is relative to the watershed. Not exactly equal based on some of the hydrology and landscape factors that we've identified as being critical to driving those baseline loading conditions. So going from, the entire watershed, we talked about that 590 metric tons of reduction that we need. In Ohio, we're developing a plan for 442 metric tons of reduction. We've identified kind of specific ways that we'll achieve reductions within the point source community. And, a lot of that is through additional work and ongoing implementation of long-term control plans, ongoing work in the stormwater community, and ongoing work with our household sewage treatment systems. Now, the non-point source side is something that we've a lot of emphasis on, is that, the non-point source is not just sources of phosphorus. The non-point source encompasses also phosphorus sinks. So as phosphorus moves across the landscape, as water moves across the landscape that's carrying phosphorus, some of it's lost, it picks up some, moves across the landscape through the stream channels. It's a dynamic process, and there are opportunities to enhance those sinks across the landscapes, be that through developing more effective drainage channels with two-stage ditches, developing wetlands, developing floodplains that were historically disconnected from the watershed, and even just other stream restoration that gives some of those natural functions back to our stream channels that we've historically modified. But the largest share and the lion's share of the effort is through managing non-point sources on the landscape. So we kind of look at it in a few different bins. We look at it, we need to manage nutrients. What's our source of nutrients? We need to manage commercial fertilizer. We need to manage manure. We do still need to manage erosion. We have a component of our soil particulate phosphorus is bioavailable. So we need to still be cognizant of erosion. As we've seen these changes in hydrology, we need to be increasingly aware of managing water. That management practices don't just target sources, but target the volume of water coming off the landscape. Look for opportunities to reduce it, or at least slow it down as it moves across the landscape. And also, there's a lot of, there are new technologies out there that we don't have fully built into our suite of BMPs that I think we would expect to be important. Some of those are these water management ideas. We have cascading waterways. We have a few of those demonstrated throughout the state. See some promise there. We have water reuse systems that people have piloted where we can capture some of the drainage and use it to irrigate a crop later in the growing season when we typically run a water deficit. So there's some opportunities there to potentially really hold some of that water back on the landscape. And with legacy phosphorus, we're seeing improvements in both identifying where the high soil test phosphorus is, and also the type of technology we can deploy on the landscape to remove it. So we're seeing those technologies emerge, and that's something we need to understand, that we may not know every single BMP that's going to get us to where we need to go today, and that we're going to continue to look for new opportunities moving forward. Yeah, so we have to talk about a little bit more specific on stormwater. We have different mechanisms that we can look to manage it. They're similar to non-point sources. We have we can look at source control. With non-point sources, it's nutrient inputs often, but on the stormwater landscape, it's often the things that are landing on our impervious surfaces and getting washed off because we kind of short circuit that water movement across the landscape. Water management is still important. Impervious surfaces increase flow volume, and trap and treat practices are still effective in the stormwater world. We're proposing working with our existing permitting mechanisms and really how we've identified so that the reduction we're looking to target is from the MS4 communities, our largest urbanized areas that have that permitting mechanism in place, and how we've really laid out a strategy for implementing TMDLs through that permit. And then, moving forward, this TMDL would then be kind of captured in that permitting umbrella. So you're really looking at ongoing progress in those communities. And one thing that I think we'll need to look at as we work through that permitting mechanism is that we are very specific and focused on total phosphorus in our MS4 permitting, and that we should consider if there are different BMPs that would have a greater impact for managing dissolved reactive phosphorus. So revising that permitting scheme to maybe focus a little more on dissolved reactive phosphorus moving forward.
With our treatment facilities, we've set our goal at managing existing loads from the facilities. This goes along with continuing the implementation of long-term control plans where substantial reductions in load from wet weather discharges are expected. And ultimately, we need to have a plan for growth such that we can manage the existing loads while continuing needed expansions in the watershed. To do that, in the PMR, we've identified several opportunities for managing those loads. One is through the use of better technology for new, expanding, or replacement facilities. Two is through ongoing optimization. And finally, there are opportunities to improve source control through the pre-treatment program. In order to manage the existing loads from our treatment facilities, we're proposing to develop a watershed general permit for phosphorus. This is a tool we can use to maximize the flexibility for managing these existing phosphorus loads. Here we would be looking at kind of an umbrella permit that allows us to implement the limit as a seasonal loading target for the larger group of facilities, or a grouped loading target. And within the permit, we're proposing that we would include the 35 largest treatment facilities that contribute 85% of the load from all facilities in the watershed.
The list of all of those 35 permits and a lot more information about that general permit are concept, I should say. Not a lot of information about what the permit would look like, but conceptually what we would look for to be in the permit are in the report itself. On the non-point source side, we kind of built a plan kind of following kind of three big categories. We have water quality planning. We also we need to understand where policy fits into the TMDL and implementation. And we need to understand, and then we look for how we facilitate implementation. So water quality planning, as we develop these plans, we've identified that there are some specific things that we need to be kind of aware of as we continue developing plans for phosphorus reduction. We're going to need a lot of implementation. Most of the modeling shows us that, 2/3 or more of our acres need to be using, a suite of BMPs to really kind of get us to where we need to go. So we just need to kind of understand that, implementation it needs to be very widespread. We also know that DRP is going to be the harder thing to tackle. If we were just targeting total and particulate phosphorus, the BMPs are more developed based on our historical focus on them. And, it's easier to trap and treat those sediment particles. No single BMP is going to get us to where we need to go. And also, we do know that there's heterogeneity across the landscape. We know some fields, some portions of fields, and some parts of the watershed may contribute more. So we need to consider how we might target those areas with the right BMPs for why that's occurring. And that would get us to our goal more efficiently. And we need to keep our eyes open for emerging practices and opportunities to do things that we haven't fully developed today, but are emerging from ongoing research. So we have two pre-existing kind of planning mechanisms. Our domestic action plan built a lot of the framework for implementing non-point source reductions in the Western Lake Erie Basin. And from there, we look to our smaller watershed planning tools, our 9-element non-point source implementation plans, where you can kind of really hone in and look for opportunities on the landscape. So I said we need to kind of understand where policy fits into the TMDL world. The TMDL doesn't give us additional authority over non-point sources. So, there's no trigger for a change in policy because we're developing the TMDL, but policy changes do happen. We kind of document some of those that have happened over the last 20 years in the report. And also new regulations happen. So both things happen. So new laws and just kind of new policies and how we understand things and how we go about implementing them. Because the TMDL doesn't trigger those, we just need to be sure that we have enough flexibility in our implementation plan that as those changes do occur, that we can implement them. And then to try to save a minute for questions, I don't want to go through this in detail, but we really rely on the community and all levels of government being engaged in trying to manage phosphorus. So we have highlighted state-focused initiatives, federal initiatives, I think most importantly, local initiatives, because that's where change really happens. And the nonprofit organizations and voluntary actions, lots of things going on, lots of people focused on this problem. And the better we can kind of integrate all of this work, the more effective we'll be at kind of getting where we need to go on the non-point source side.
So this is the email address if you have any other questions that we weren't able to get to today. So please, forward those questions to that email address. And we want to thank you again for coming. And for those online, we want to thank you. And for those in the room, drive safely home. Thank you.